Hello students, in this video we'll discuss about peephole optimization. So in the last video we have discussed about optimization of basic block, like what are the optimizations we can perform on a single basic block, and what are the flow graph, right, and dominators, loops. So those things we have discussed. And what does it mean by peephole optimization and where it comes under, so that we'll discuss. So first, what is mean by optimization? See, optimization is nothing but reducing the code in terms of cost or in terms of time or in terms of, right, space, means the number of instructions or the memory. See, the optimization techniques, whatever we have used, right, common sub-expression elimination, they are going to be redundant and they are going to be applied in different places. So based on that, we can divide this optimization into mainly two types. One is global optimization and another one is local optimization. So what is mean by global optimization? If it is a large program and we are dividing into blocks, and those basic blocks can be constructed as flow graph. See, if you perform the optimization on more than one block or complete program, then we can call it as a global optimization. Mainly, the machine independent optimization is called as global optimization. Of course, that doesn't mean that we can't perform the global optimization in machine dependent, but generally, right? So we call machine independent optimization is called as global optimization. And local optimization means we are going to apply it on blocks. So if an optimization is performed on a single basic block, then we can call it as a local optimization. So for example, let me take a simple example of local and global. So assume that if I'm having like this, a equivalent to 10, okay, so b equivalent to 10 plus 20, and we have these two statements here. So now these two are constants. So if you want to fold this, we can evaluate this at the time of compilation by rewriting the statement as b equivalent to 30. To evaluate this, I didn't consider any other basic block. So this is called local optimization. So for example, somewhere we are having like this, b equivalent to a plus 20, right? So here we don't know what is the value of a in this basic block. Then what you have to do, you have to consider the another basic block, that is a here, block 1. So here assume that the a value is constant int. Assume that it is a constant int. So if it is a constant int, you cannot change the value of a. As you know that it is constant at the time of compilation only, and wherever you are having the a, that can be replaced with the 10. This is called constant propagation, the method that we'll discuss anyway. So now see here, to optimize the basic block 2, we have used the code of basic block 1. Then locally we can apply this. So to perform b equivalent to a plus 20 to 30, to perform this optimization, we have considered more than one basic block. Then we can call it as a global optimization. If you perform in local, that is called as, I mean, say that only one basic block, local. So mainly the peephole optimization is a best example for the local optimization. That doesn't mean that it is the only one like this. So we have so many, but peephole optimization is the best one for local. So what is peephole optimization and what we are going to do, that we'll discuss now. See, optimizing the target code of a block, a single block, as I told you. So which is done by examining a sliding window of targeting instructions. So the main aim of this, the main behavior of peephole means sliding window. Means, for example, if you are having a whole code like this, okay, so we are going to focus on the window of it. So this is called peephole. Just throughout the code we are taking some. So the sliding window we are considering perform the optimization. Then what are the techniques we are going to use in the peephole optimization? See guys, we have this algebraic simplification, redundant instruction. We have already discussed, but all these things, what will take, how it is going to be utilized in the peephole optimization also. So first we'll go for the redundant instruction elimination. For example, so this we are performing it on the target code. We can call it as a machine dependent, and this we are performing it as three address code or some pseudo code. We can say that this is machine independent optimization. See here, the which is redundant here. If the condition is true, we are going to perform the A plus B. So if the condition is false also, we are going to perform the A plus B. Okay, so then what is the need of writing this much code? Simply you can write here x equivalent to A plus B. There is no need of a condition also. So the whole statement can be reduced like this, x equivalent to A plus B. So first of all, we'll get a doubt like who will write such kind of statements? Generally, we won't write it. So while you are converting the code into three address code, sometimes there may be a possibility of having like this because of some limitation of instructions available in the assembly language statements. So then it will be execute, right? So just here we are giving this example to tell you that what exactly the redundant instructions. Then coming to the code, target code generation, see this we have already discussed kind of questions. Move R0 comma A and move A comma R0. What is the need of doing like this? Moving A to R0 and R0 to A. So this is also redundant instruction. And we have discussed in the previous video that so generally we are storing like this. So store X comma R0. We might have the R0 value we are storing in X, and immediately for some other purpose we are bringing the value of X to the R0. So again, this is a redundant instruction. So these kind of things can be eliminated by using this. Then the next one is flow of control optimization. So sometimes we need to perform some unnecessary jumps. For example, see this, go to L1 and then from L1 we are going to L2. So if you are having L1, we are not executing this code, then we are going to L1 here directly because it is an unconditional jump. From here directly we are going to L2, right? So wherever we are having the L2, then what is the need of doing such a, right? Here we can, so directly write, go to L2. So directly we can jump from the, means directly we can jump to L2. So because in L1 also we are mentioning that go to L2. So what is the need of writing go to L1 and go to L2, the redundant? So directly here only you can write go to L2. Automatically it will jump to that. So this is the unconditional jump. So in conditional jump, this is another example of conditional jump. So assume that. So if A is less than B, we have to go to L1. So L1 is go to L2. So there also you can directly write it. If A is less than B, go to L2. So there is no need of going to the L1 then going to it. So it's a useless and sometimes it may require memory. Okay. Then coming to the next one, algebraic simplifications. See, this we have already discussed algebraic simplification, just reducing the means we if there is any possibility of simplification we are doing it. Simplification is just we are transferring the code to another so that we are going to uh, reduce the cost of that program. For example, here we are performing x plus 0. So we have to use some OR gate to do it. So instead, we can write simply x equivalent to x plus 0 means you no need to write it, just we can remove it. No need to write something. Okay, if you can write x equivalent to x, what is the need of this? So it is nothing but x. You can simply remove it. And in such cases, even x equivalent to x into 1 also. These kind of statements, at least we can remove it. Sometimes we have to reduce the strength of it. So this also comes under the algebraic simplification. What does it mean by reduction in strength? See guys, for example, if I write like this, x equivalent to x into 2. So can be written as x equivalent to x plus x. You may get it out. Why? What is the need of doing it means? See, star is the high cost operator than the plus. Then you may get it out. Who told that? Right? How you can prove it? See, for example, assume that x value is 5. Then 5 into 2, the final x value is 10 only, right? Okay. So then we'll go for it. So here also it would be same. Then how can I do it with a plus? How can I prove that plus is least, right? For example, what is the binary representation of 5? 0, 1, 0, 1, and we are multiplying with the 2, 0, 0, 1, 0. Do it. So 0 into 1, 0, 0 into 1, 0 into 0, 0, 0. For 1, 1 into 1, 1, 0, 1 0 multiplication 0 you have to write, again 0 you have to write, so 2 times. Okay, sorry, you have to write here. Then you take it 0 0 plus 1 1, 0 plus 0 0 plus 0 0, 0 plus 1 1 1, so 0 0 0 and 0. Total how many times we have added here? 1 2 3 4 5 6 7 8 9. We have added 9 times like this. 0 plus 1 0 plus 0 0 plus 0, like that we have performed 9 additions. So we need 9 OR gates. But here if you represent the same code with the plus, so what is the binary representation of 50101? Finally we got the 10 here. We'll check whether we, if we perform it also we'll get it. So 0101, listen here guys, 1 plus 1 1 0, the carry will be forwarded. So we have performed one addition. 0 plus 0 0, 0 plus 1 1, 1 plus 1 1 0, the carry will be forwarded. 0 plus 0 0 plus 1 1. See, we got the same result. But how many additions we have performed? 6 additions only. But here 9. Like that we can do it. Not only this, even we can less. We can even reduce the cost of plus by writing x equivalent to x right shift to 1. So means what is the binary representation of 5? 1 0 1 0 1. Right shift means 1 0 will be removed, 1 0 will be added. Right shifting. Okay. Sorry, left shift. Left shift. Left shifting. Then what will be happen? 1 0 1 0. See, we got it. Like that, if I perform 2 shifts, then that would be multiplied by 4. If it is 3 shifts, multiplied by 8. For example, you can write it x equivalent to x into 8. Okay. So can be reduced with x equivalent to x left shift 3. So for example, let me take the same 5 here. So 0 1 0 1, then you perform 3 shifts, right? So add 3 zeros right here, then 3 zeros removed, then 1 0 1 triple 0. This is nothing but 40, right? Like that we can do it. Means somehow we can do the reduction here. So if it is divided by, we can perform the right shift. If it is multiplication, we can perform the left shift. Means, for example, if you are multiplying the value, so which can be represented by 2 power n, okay, x into the number which can be represented by 2 power n can be shifted with n bits. If x is divisible by 2 power n number something, then we can write x right shift n bits. Like for example, you are dividing the x with 32, where the 32 is represented by x by 2 power 5. Then simply you can write here x right shift 5 bits. We can do that. So that is called algebraic simplification. So then the last one is use of machine idioms. See, this is completely machine dependent one, the machine idioms. See, for example, if it is I equivalent to I plus 1, can be reduced by I plus plus. So this is specific to the particular language or machine. In Python, we don't use it. In Java and C, we use it. In Fortran, we don't use it. Depends. Okay, I equivalent to I minus 1 can be represented as I minus minus. Depends on the language, right? And we have another one called unreachable code. Sometimes the code would be not reachable. For example, you take it, go to L. Directly we are going here without any condition. Then this code is unreachable code. We can remove it directly. Because unconditionally we are jumping to here, right? So we can simply remove it. For example, if it is a condition, if it is true, go to this, otherwise go to this. In that case, it is not unreachable, but this is. So such thing which is considered a particular basic block, that is treated as local or peephole optimization. So in the next video, we'll discuss about register allocation and attainment.